Welcome everyone to Thermodynamics. Today we're going to be covering the first law, energy balances, the four fundamental processes, and a lot more. So let's get into it. So thermodynamics concerns ourselves with energy, okay? And the first law of thermodynamics, why don't we go through all three laws of thermodynamics? Law number one, energy is conserved, okay? And we have an accompanying equation for that we are going to talk to once I'm done listing the laws of thermodynamics. 2, the entropy in the universe tends towards a maximum. The entropy always increases, okay? You will never see equations concerning entropy in any algebra-based thermodynamics course. You will only see this in a calculus-based thermodynamics course, which is only really taught to chemical engineers and mechanical engineers in college. Then third law doesn't actually say this, but this is what you're intended to interpret by reading the third law. You can never reach absolute zero. Okay, if you want to know word for word what the third law says, it says the entropy of a perfect crystal at 0 degrees Kelvin is 0. Okay, if that doesn't make sense to you, it shouldn't. Anyway, I'm a chemical engineer, that's why it makes sense to me. Let's get into the first law of thermodynamics, which is what you are ultimately going to be basing your entire course around. The change in internal energy equals Q plus W. Let's bring that down here. What exactly does that mean? Okay, internal energy is the energy of a system. Okay, so first we need to talk about exactly what a system is. We can have an open system. An open system is a system where mass and energy are allowed to flow in and out of your system. This is open. You see, it's an open container. You can have an closed system. No mass flows in or out, but heat can flow in and out, but energy can flow in and out, okay? So you apply conservation of mass to this one, and finally you have the isolated system. And this is a box with like insulation around it. No energy can flow in or out, no mass can flow in or out, okay? In an isolated system, the change in internal energy is always 0, okay? You cannot change the energy if no energy can flow in or out. The energy is always constant, energy is conserved, okay? So for the overwhelming majority of problems you're looking at, you're going to be looking at an closed system. To deal with this, again, you're going to need to use calculus if you're taking thermodynamics in college. So internal energy, as you can infer by looking at the name, it is the energy of a system. It is the internal energy of stuff, of gas, of fluid, of a solid that's in your system, okay? We're largely going to be working with gases here. So let's talk about what Q and W are. Q is heat, okay? You can transfer heat to your system, you can remove heat from your system. And W is work, okay? Work, there are many different definitions for work. Work, as it is in this class, is energy that can be used to do something useful, okay? If you have a piston and that piston moves forward to spin a wheel, that's work. That's the piston doing something useful, okay? If you have, if your isolated system is a battery, that battery is going to produce electricity, and that electricity could make your car wheels turn. That's something useful. That's energy you can use, okay? Heat, by contrast, is energy you can't use. I can't make my car go by heating it up, okay? I can't make the train wheels turn by just warming up the train. I can't turn on my computer by warming it up. I need to supply work. I need to supply a type of energy that I can use to do stuff. That is the definition I'm going to use for work, okay? And if you're a little bit more advanced, you can then use this definition I've just given you and say, based on law 2, the entropy of the universe always increases. It means that in every process, in every interaction, you must always convert some amount of work to heat. You must always lose useful energy. When the battery in your car turns the wheels of your electric car, your car gets hot. When I turn on my computer, my CPU gets hot. Okay? The train boiler is hot to convert coal into the useful energy to turn the wheels of the train. Okay? You will always generate heat. You will always lose some work as heat. That's the second law of thermodynamics. By this definition, if Q is positive, it means you are adding heat to your system. Okay? If work is positive, it means you are doing work on the system. Okay? Think about it this way. If you are adding energy to your system, that needs to show up in this equation as a positive number. If you are taking energy away from your system, that needs to show up in this equation as a negative number. Okay? If I use the electricity in my battery to spin the tires of my car, then my battery is losing work. The battery is doing work on my car. If the battery is my system, then the battery is doing work, which means if it's doing work, then work is negative. So it's losing internal energy, okay? Oftentimes you can figure out what sign everything is supposed to be if you just think about the problem, okay? If I have a piston and that piston moves upwards to turn a wheel, well, the wheel is gaining kinetic energy, so that energy has to come from somewhere. It has to come from my piston. So my piston has to lose energy, and if it's losing energy, it must be doing work, or it must be losing heat, okay? So now let's talk about the four fundamental processes, okay? You have 1, the isothermal, 2 is the adiabatic, 3 is the isobaric, and 4 is the isochoric, okay? Let's translate each of these words into English, because you're going to have to memorize what these means. Isothermal, you can imagine, is at constant temperature, so delta T equals 0, okay? Now, if you're dealing with an ideal gas, which you probably are, that also means that delta U equals 0, okay? Because the change in internal energy for an ideal gas is dependent only on temperature. Next, we have the adiabatic. Adiabatic says that Q equals 0. It is an insulated process that happens immediately. It happens very, very quickly, okay? So heat does not have enough time to interact with the environment, interact with the surroundings of your system, okay? So that means also for an adiabatic process, the change in entropy is 0. You may or may not need to know that. Isobaric means that you have no change in pressure. Your pressure is constant. And for isochoric, you have no change in volume. Your volume is constant. Okay? So let's look at each of these simplifications in terms of the first law. Change in internal energy equals Q plus W. In order to look at that, I'm first going to give you the equation that Q, the heat transferred to a system or transferred away from the system, equals mc delta T or nc delta T, okay, depending on what you're dealing with. This is the mass of your system. This is the specific heat capacity. This is going to be the number of moles in your system. This is going to be the molar heat capacity. Okay? So depending on whether you're given the specific heat capacity or the molar heat capacity, you're going to need to multiply that by either the mass of your system in kilograms or the number of moles in your system. Okay? So you would, of course, be given your heat capacity, and you'd have a way of finding out either the mass or the number of moles. Okay, now back to the simplifications I was talking about. So for an isothermal process, I can take my first law equation that governs everything I deal with, and I can say delta U equals Q plus W. since I know that if my process is isothermal, delta U equals 0. So I can say 0 equals Q plus W, or Q equals negative W. That's the simplification I make for process 1. In the case of an adiabatic process, I know Q equals 0, so I can write delta U equals the work done. Okay? I just eliminate Q. For an isobaric process, what I'm going to say is delta U equals Q plus W, and I'm going to be able to substitute in an equation for W. I'm going to say work equals minus P times change in volume. Q minus P delta V. Okay? And finally, the simplification for isochoric means volume is constant. In this case, work equals 0. I should write that up here. Work equals 0. So delta U is just equal to Q. And if I want to substitute this equation, I can say delta U equals MC delta T. Now let's talk about what all of these look like on a PV diagram, on a pressure volume diagram. Okay? So I've got volume here on my x-axis, I've got pressure here on my y-axis. Okay, so let's talk about the easy ones first, okay? When there's no change in pressure and there's no change in volume. Let me do isobaric in green. Isobaric means no change in pressure. It's going to look like this. Okay, I hope that shows up well on camera. I like to use very thin markers. Just for my personal use of this whiteboard, and the thicker ones show up better on camera. So this is green. This is the isobaric process. Okay, it's going to be a flat line on the PV diagram. The isochoric process, let me use red for this, is going to be a vertical line. There's no change in volume. Your volume must remain constant. Okay, this is going to be the isochoric. Now let's do the isothermal. I'm going to do this in blue. Isothermal is going to follow a path similar to y equals 1 over x. If you look at a graph of y equals 1 over x, that's going to be about the shape of this line. It's going to be a tad bit steeper, like this. Okay? And finally, the adiabatic process is going to behave, it's going to have a similar shape to the isothermal, except it's going to be much steeper. The adiabatic process looks more like 1 over x squared. So it's going to look like this. Okay? So that's what all 4 of the processes look like on a PV diagram. All right, so that is thermodynamics, everyone. If you're a college student, Meek, Chemi, and you need tutoring for like actual college level thermodynamics, come talk to me. I can tutor you, no problem. If you need extra help, go to meekextrahelp.com or join the Discord server. And if you like the video, if you believe this is meaningful, that you gained something valuable today, please like the video. Enjoy life. Have a fantastic day. You got this.